Hello. Today we will be going over the calibration of a supersonic wind tunnel. My name is Sean McKinley. In our group we have Christopher Daly, Jordan McIntyre, Ali Nyamir, and Rick Rogers. The objective of this lab is to determine an accurate relationship between the nozzle block setting and test section Mach number of the supersonic wind tunnel. This will be explained later. What is calibration? Calibration is the process of finding the relationship between the physical state of the machinery and the effect it has in terms of measurable and useful aerodynamic data. The questions we hope to answer are: what is happening to the Mach number of the flow in the test section of the wind tunnel as the block setting is being manipulated? But first, the characteristics of supersonic flow should be explained. The main difference between a body in a subsonic flow and a supersonic flow is the creation of a bow shock in front of the body. Here is a picture of a body going through a supersonic flow. You can clearly see the bow shock forming around the tip of the object. Properties such as Mach number, temperature, pressure, and density will change across a bow shock. We can measure these changes. For this lab, we will assume that the entropy remains constant across a bow shock. Here is a picture of the supersonic wind tunnel we will be testing on. It's located in the High Bay Labs at NC State University. Here's how it works. The wind tunnel pumps pressurized air through a nozzle to create supersonic flows. There is a glass-enclosed test section where we can conduct experiments. The pressure of the flow is controlled by a control block seen below. However, the exact relation between the block position and the Mach number in the tunnel is unknown. Luckily, the tunnel has two pressure ports forward and aft of the test section. As we will explain later, we can use these readings to calculate the Mach number in the wind tunnel. The experiment. For this experiment, we placed a pitot tube in the test section. We ran the test section at various block numbers, and we took pressure readings in front of and behind the bow shock that formed around the pitot tube. For this lab, we predicted that the Mach number would decrease as the value of the block position increases. We predicted this because we believe a low block position corresponds to a low pressure in the tunnel, and according to Bernoulli's equations, shown below, there should be an inverse relation between pressure and velocity. Bernoulli's equation states that 1/2 rho v squared plus p is constant, where v is velocity, rho is density, and p is pressure. So if these values are constant across a tunnel, there should be an inverse relationship between the velocity and the pressure. As pressure increases, velocity decreases, and vice versa. Here are the results of the experiment. These graphs show the two pressure readings for each run of the wind tunnel at various block settings. By the dynamics of the wind tunnel itself, the pressure increased for a while initially before decreasing, and we took the maximum pressure reading from each pressure value. Here are the rest of the results. Using these readings, we can calculate the Mach number of the test section for each block setting by using the Rayleigh-Pitot formula shown below. Solving this equation for Mach number at each dial setting, we get the following values. Finally, these Mach numbers will be used to create a calibration curve for the supersonic wind tunnel. As you can see, as we expected, the Mach number decreases with the pressure as the pressure increases. However, there's a slight dip around halfway through the pressure readings. This may be for a variety of reasons. But in conclusion, we now have a rough idea of the relation between block position and Mach number in the wind tunnel. These results can now be used for later experiments. That concludes this lab, the calibration of the supersonic wind tunnel. Thank you for watching.